Hello, everybody. Welcome to this machine learning session, machine learning operation. As our first presenter, we're going to have Deepak from ESR, who is going to be talking about building machine learning ops pipelines for Lumi drug scan. Over to you.
Good afternoon, everyone. I hope I'm audible and visible. Yeah. So good afternoon. So my today's talk is building an MLOps pipeline for Lumi drug scan, a real-time drug screening system. So who we are? I work for ESR. I'm a data scientist at. Just 1 second. I think I'm getting an echo, so I'll just mute. Yeah. Yeah. So yeah. So ESR is a Crown Research Institute with approximately 470 people working at 5+ locations across New Zealand. And our core purpose is to contribute to the economic, environmental, and the social well-being of people and communities across New Zealand. And we do this by delivering enhanced scientific and research services to the people towards the public health, food safety, and the justice systems, and the environmental sector as well. The forensics science at ESR is a key service provider to the New Zealand government, and with our deep knowledge in drug analysis field and expertise in forensics, we are the source service provider to New Zealand Police and NZ Customs. We have exclusive access to the illicit drug samples in New Zealand. We can store them, we can even manufacture them, and that puts us in a place where we could develop machine learning models which are related to the drug data. The illicit drug problem is a huge problem across the world. For example, 10,000 samples are intercepted in New Zealand alone. Australia, 1 sample is intercepted every 5 minutes. And in US, 70 tons of meth was confiscated in year 2018. The crux of the problem is that thousands of unknown samples are intercepted every year, but the police or the infrastructure does not have the ability to analyze all these samples. The reason being the current methods are really unwieldy, they're cumbersome, expensive, and in many cases not accurate. The forensic lab analysis is reserved for a selected cases which go to the court, and also the health and safety of concerns of the people, particularly the New Zealand police who deal with it, is a serious concern. Furthermore, the on-field decision-making relies on the circumstances and the training and the experience of the police personnel, and it is not really informed by the scientific evidence. So the approach to solve this problem for us was to collaborate with New Zealand police, utilize their frontline knowledge, and then combine that with our expertise in science, particularly in the drug space, and be able to come up with a system which helps them in making evidence-based and informed decision making. This is a rough diagram of the developed solution. So the police personnel encounters a drug sample on the field, and they use a portable spectrometer, which is an important component of the system, to scan and get the spectrum of the sample, which is the device is interfaced with a mobile phone. So the scan is passed on to the mobile device, which then, with the help of a drug scan app developed by ESR, uses the online cloud service to classify the drug into a specific drug or a harmless substance. And then a report is sent to the police personnel for further work on it. So initially, the typical process consisted of police doing a search, identifying the substance, and using their past experience in making the decisions. However, with Lumi as a decision-making tool, this now is more scientific and presents a lot of weight to the actions which the police can take at that point in time. So the core of building the system is an ML-based drug classification model, which is essentially done with the help of these steps. The first is the data acquisition methodology, and this, in fact, is the most important step. Followed by that, the research and development of machine learning models, and then pilot testing and validation of ML models with the help of police and internal drug team, which again is extremely crucial. Followed by that, the productionalization of the ML models and the continual monitoring and maintenance of these models. So you can see that this practically covers every aspect of a commercial data science project. In this talk, I'll focus on a few key components which we had leveraged in making this project a success. The key components are, firstly, tracking the data and the model. We use a number of tools to do that. The second, intelligent data acquisition, which is extremely important, particularly for this project. And finally, interpretability and explainability of the machine learning models which we developed, which has helped us in a number of ways. So moving on to model tracking, as I was talking today morning, this is just an elaborated diagram of that. So you can see that this is a crude representation of the machine learning process which we follow. So here is the database. Creating this database itself is a challenge because we get drug data samples from a number of different sources. Many of them could be duplicates. Cleaning them and adding them to the database, taking into account the missing values and stuff like that. This database is not accessible to the data scientist. It's managed by a different team. Data scientists come up with hypotheses. For example, maybe let's try an experiment where we compare two particular drugs and see how the machine learning model can classify them. So we come up with a number of different hypotheses, and based on those hypotheses, do the data extraction from the database, and then using our machine learning experience and help from the domain experts, that is the drug scientists, we try to transform the data into features. So this aspect of extracting the data, cleaning it, and then transforming it into appropriate features almost consumes 90% of the time and resource in doing these experiments. So after a number of such experiments, we create a large number of models. The key thing is to be able to track the complete process as to which version of the data was used for which transformation, and the final model and the different versions of the model corresponding to different hyperparameters, how to maintain them. That is a very crucial task for us, particularly if we want to maintain the objective of achieve the objective of data provenance, as to track. For example, if model M1 is something which we are interested in, then what data was used to, or what subset of data was used to actually arrive at that model. Say that after this whole process, we find that the model number 4 is the one which is the best. Then what we essentially do is take this complete thread out of this and execute it separately, and incorporate this into our production and serving system. So this, there is a clear wall between the two steps, the experimentation and the productionization, which is actually crucial for maintaining our models and ensuring that we do a seamless job in serving. Regarding another point about data provenance, assume that there is a database update when we are actually going through these experiments. It is important to track the update both in the database as well as throughout this whole thread. We do that again with the help of tools like data version control and ML flow. Basically, ensuring that we comment each and every task which we do and ensure that the versions are properly updated. Summarizing, tracking is actually extremely crucial for ensuring that our ML is reproducible. Not only that, we also separate our input, model, and transformation code. We ensure that each of them is handled separately, especially when we have multiple data scientists collaborating together. And also we ensure that each of those aspects is containerized separately. So for example, a drug scientist might be very good at R programming language, whereas another data scientist might be using Python. So in order to enable seamless collaboration, we have a separate container for each of these tasks, and we have a workflow where we integrate the output from each of those tasks separately. Finally, we heavily use hashing design pattern. We, for example, splitting the data sets into training and testing set relies on hashing. Also, feature handling is again done using hashing. So we heavily rely on good design patterns. The second crucial component of our work is active learning. So as I mentioned, uh, drug analysis and coming up with the ground truth is an expensive task. So labeling each and every scan might take hours for the forensic scientist and for the technician, and it takes a lot of it incurs a lot of cost. So active learning is a subset of machine learning where you can, by choosing the right data, you can actually learn a very good model even with fewer labeled data. And it is especially useful when the data is expensive and the acquisition process is slow. Also, it deals with problems like imbalanced data and helps achieving in the target metrics. We especially have a lot of imbalance in data because not all drugs are equally popular. So we need to take leverage active learning for that purpose. And finally, the very crucial component is explainable AI. So when we are generally developing machine learning models, we have say a model A, and then we come up with a model B, which is better than model A in terms of various metrics. But what we don't consider is what is the impact of model B on the end user. Because for a machine learning project to be successful, trust is a very key factor. And things like bias, fairness, explainability, etc., needs to be considered. Typically, an end user who is using AI in a decision-making system, they tend to um, build a mental model based on the behavior of the machine learning model. So for example, if the police personnel is encountering a particular substance frequently and they use the system, the machine learning model to classify it, then they have then they have a mental model, an expectation that the system will behave in a certain way. But what happens is that when a new model, say a model B, which has got a better accuracy, is deployed, uh, the it is going to have a different behavior, and it is going to have it is going to affect the way uh, the trust of the end user. So if you take this example, this explainability charts are from state of the art SHAP algorithm, which is used for explainability. So you can see that the on the y axis we have features, and they're ranked based on the importance of these features in that particular model. So if you take model A, then the features 0, 1, 16, and 2 are the top 4 useful features. Whereas model B, which is better than model A, ranks 2 over 16. So because of this subtle change, there are going to be some differences in the way the model behaves on the field. So even though model B is more accurate, using explainability, we also need to ensure and understand as to what has actually changed in model B, which makes it better, and how it is going to affect the behavior of the model when it is interacting with the end user. So this is an important concern which we also take into account when we build our models. So to conclude, these are the three main components which we have incorporated in our MLOps cycle to make this project successful. Thank you. Thank you for listening.
Excellent. Thank you, Deepak. So encourage people to put some questions on the live Q&A. In the meantime, maybe I have a few questions. Can you say something about the size of the data? Are we talking here about gigabytes, terabytes of data?
It's definitely not in terabytes. It's definitely a few gigabytes of data. We have millions of scans in our database for at least 4 to 5 drug candidates.
Excellent. Just maybe as a clarification, who is actually running the pipeline? I mean, is that somebody who's a machine learning expert, or have you been able to sort of move the whole pipeline over to somebody who's not a machine learning expert and can then use it?
The pipeline is essentially run by machine learning experts, and we also have a group of software engineers who assist us in building this pipeline and maintaining them. So it's definitely worked on by experts who have a good background in software.
Excellent. I see two more questions actually arriving here. One is from Daniel Bentel. He asks, how have you implemented active learning? I think you talked about, some rare events and the need for active learning.
So for active learning, essentially what we do is active learning basically is a cycle. I probably didn't explain the whole thing in the interest of time. So when you have an initial model and a data set which you are supposed to label, you have a large different methods to identify which scans or which data points you should be labeling, which would essentially help you in improving the model. And one of the ideas is to see the uncertainty associated with the data point. If the data point which has got more information or more entropy in it, which can assist you in getting a better model, then you tend to prioritize that for labeling. We also, of course, use domain experts information. For example, if somebody tells us, if the drug expert tells us that the combination of these two drugs or combination of this impurity with this drug is going to create a spectrum which would be difficult for the model to learn, then we try to prioritize that in our algorithm.
Excellent. Thanks a lot, Deepak. There's one more question. I may actually ask you to answer that question offline. That's from Roland, if that's okay. In the meantime, I think I'd like to welcome Jan Schindler, who is going to talk about, maybe you are able to share your slides at this point, Jan? Yeah. Experiences developing an operational workflow for large-scale instance and semantic segmentation of remote sensing imagery using CNNs or convolutional neural networks. Thank you.
Thank you, Alexander. Yeah, my name is Jan Schindler. I'm a remote sensing and data scientist at Manaki Whenua Landcare Research, which is one of the Crown Research Institutes in New Zealand. And apologies for the long title. I would basically like to share with you some of our experiences while we were developing this operational workflow for deep learning operations on remote sensing imagery. And I would like to thank my colleagues as well, in particular Brent Martin and Alexander Amies, who have been also the brains behind some of the model and pipeline development. Convolutional neural networks offer nowadays great opportunities for improved mapping of land cover, change, and also mapping individual objects in remote sensing imagery compared to more traditional approaches like, for instance, object classification in imagery using machine learning algorithms such as random forests or support vector machines. And at Manaki Whenua, we host and also work with a wide range of geospatial datasets that are basically ideal for such deep learning tasks. And this includes, for instance, the spatial land cover database, all sorts of environmental layers, sol maps, a great archive of Sentinel-1 and Sentinel-2 satellite imagery, 3D LiDAR data and rasterized metrics thereof, such as canopy height metrics and elevation metrics. And over the past year or so, we really applied deep learning to a number of projects to effectively get better spatial predictions and also to discover new patterns and to automate also some of our existing processes, which are sometimes manual labor that can take days or weeks. And we are also leading a data science program that tries to explore the use of new deep learning techniques to improve our detection of individual trees and segmentation of individual trees in remote sensing imagery. So we developed a pipeline over the last year or so that sort of evolved with each new experiment and project that we tried it on. And so there was for us a real need to have a flexible and operational workflow for mapping exercises at the very local, regional, and especially also on the national scale. So if you take a step back and ask, you could also ask the question why we are not just using existing open source deep learning pipelines. And there are great examples out there on GitHub, for instance. And I'd like to mention, for instance, Solaris and Raster Vision. Those are two packages that try to do this job, and they are really good. And there are lots of benefits in using them. For instance, they're optimized for geospatial imagery. You don't have to worry about data processing. They have come with great documentation, and they already have built-in models for image chip classification, object detection, and semantic segmentation. However, this also comes at a cost, and there are a couple of downsides in practice when we I try to use those packages. So in general, they have a very large code base, which makes it sometimes it makes it effectively quite difficult to extend it or to customize it for our specific needs. It can be also cumbersome to set up, especially on a NZRSE HPC environment, and you are sort of locked into specific package versions that the authors chose. And it wasn't really ideal for our specific data and infrastructure needs. So we developed a package called DeepSeg, which is for us fit for purpose for different projects. It's a reusable software pipeline that runs on the NZRSE HPC and also on our local computers with GPU support. It allows for quite flexible training from geospatial layers and also large volumes of remote sensing imagery. We implemented a couple of nice features that were quite important to us. For instance, that it works well with our geospatial raster format of choice, which is the Kia format. It also keeps the inode usage, so the number of files on NZRSE in your project space at a bare minimum, and otherwise you run into project allocation issues, which is no good. And we also implemented a couple of other nice features that I will talk about this in the following slides. So we focused on two deep learning techniques. The one is instant segmentation of objects. And here we used a very popular implementation of mask RCNN. And the other technique is semantic segmentation. And we use the UNet and ResUNet neural network structure for binary and multi-class segmentation of imagery. The overall workflow of our pipeline is fairly straightforward. So if you have a stack of imagery, for instance, satellite imagery alongside with to get maybe also elevation data, and alongside that you have training labels. Those could be in a raster format or in a vector file. So in the first stage, basically they are processed and tiled up into small image chunks. I will talk about this later. The next stage is a training stage. Then we have a cross-validation stage with error assessment, and then finally the prediction stage. So fairly straightforward at this point. It's also fairly easy to install on your local computer, on NZRSE, and also if you like in a Singularity container or Docker container. So here you see that it's basically just fairly standard Python packages that we are installing. On NZRSE, it's process a bit simplified because you can just load the appropriate modules for CUDA and to make use of the GPUs on NZRSE. And for your local computer, you still need to install the appropriate libraries. But everything is quite nicely orchestrated with the Conda within the Conda environment. So we try to keep the number of files and the overall structure really simple so that we can easily understand it, and others who work with this code can also extend it quite easily. From a user perspective, the user who wants to run experiments doesn't have to understand the code itself. They just really have to edit one file, which is an experiment.yaml configuration file. And the user can easily create more experiments with different configurations, and he or she can make use of an extensible model zoo. And this is how the config file looks like. So you can, for instance, choose the various stages that you want to run. You set your model parameters, and you also point to the location of your geospatial rasters or vector labels. The way we structured the pipeline is that you have one central orchestration bash script, and this bash script can be run directly locally, or you can just submit it as a Slurm batch job on NZRSE. And yeah, the documentation on the NZRSE support site was great for this purpose, so this works really well. You can also run each step, training stages, for instance, individually, if you just call the appropriate Python module directly. At the data preparation step, we first rasterize all vector labels and then create a consistent grid overlaid over the entire study region with overlapping vector tiles. And those vector tiles are then intersected with the original vector labels or raster labels to only choose image chips that actually contain your training labels. So, and each image and label tile is then stored into just one large HDF5 file. So it doesn't pollute the environment. It's just one large file instead of thousands or even sometimes hundreds of thousands of tiny files. And this data file can be actually reused in multiple experiments, which is quite nice. I can also recommend to calculate online statistics for data sets that are larger than memory. And this is important, for instance, if you need to standardize, which you have to standardize your imagery and scale it before you can actually use it in a deep learning model. The training stage is mostly based on TensorFlow-based routines. We just had to add a couple of custom scripts and functions, and also generator classes to ingest our image and label tiles from the HDF5 file. Mask RCNN was a bit more difficult to incorporate because we had to do some refactoring in order to make it work under TensorFlow version 2.4. And we also created a custom dataset class to work with our HDF file data file. And that's actually one of the main problems with using external packages. They mostly ingest training labels in standardized formats such as the COCO annotation format, which basically would create for each tile couple more small files, and that quickly adds up for large projects. So we really try to keep it simple and store everything into one large data file. We also do image augmentation, and in relation to geospatial rasters, you have to watch out for a couple of caveats, and for instance, avoid smoothing effects during rotation and so forth. So this is also fairly standard. We also get an immediate training feedback with log graphs that are exported as image files after each epoch, in addition to the more interactive TensorBoard experience, which I found quite good. At the cross-validation step, so that's basically the stage where you run your prediction, your trained model, on unseen image tiles. And then here we get a nice error visualization by checking the performance of our model. And you can see, for instance, the true positive pixels and false positive pixels. In this case, the model actually performed quite well for segmenting individual trees in Wellington here. At this stage, we also get quite detailed accuracy statistics and error reports, which is quite useful for evaluating your model. For the prediction, we use the same prediction routines for both instance and semantic classification. It is a GDAL and raster.io based workflow, and those packages are really great. And it basically does an on-the-fly processing of extremely large raster files. And just a couple of recommendations. Yeah, you should choose your batch size depending on your memory requirements, and also choose a tile overlap based on basically the largest objects that you want to detect. And from experience recently, really consider simplifying your polygons that you create to avoid extremely large vector files. So you can easily end up with a 3 GB geo package, and you could easily reduce this to just a 200 megabyte geo package by simplifying it without actually losing information. I also like to add predefined color maps that makes it quite easy. So we also store the prediction probabilities per individual class, which basically gives you a really nice spatial prediction with uncertainty, some sort of uncertainty estimate. Now I'd like to show you a couple of examples and experiments that we ran. In this case, I ran an individual tree detection, so an instance segmentation of individual trees on aerial photography at 10 centimeter for Wellington. I used we have around 446 tiles during training stage at an image tile size of 1024 times 1024 pixels. The prediction is then run on roughly about 60,000 tiles. And the number of objects, so trees that we detected, is over 500,000 actually. So if we overlay this here and keep on zooming in, you see that the prediction also works pretty well for urban trees. Another experiment was I looked at 3D point clouds and used the LiDAR-derived classes of individual objects and turned this into a 2D representation into ground, tree canopy, and buildings. And I tried to replicate this by just looking at aerial photography with a semantic classification neural network. And this is the result. It also looks pretty reasonable. And a couple of other experiments that we ran. So we looked at mapping landslides using multi-band worldview imagery. We mapped land cover based on our LCDB land cover database as training and multi-band Sentinel-2 imagery. And another experiment was looking at forest destocking, so harvesting of plantation forests using multi-band Sentinel-2 imagery again. And the accuracy is quite high. and the remaining errors are really difficult even for humans really to distinguish or to assess. So we are pretty happy with that result. Well, the next steps for us now are really to expand our pipeline to a couple of other domains, such as cloud segmentation and imagery, for instance, and also to think about how to incorporate temporal neural networks into our pipeline. And yeah, just keep on improving the performance of our models and our workflow, with more recent and models that are published. So thank you very much.
Thank you very much, Jan, for the excellent presentation. This is time now for questions. So if people have some questions, please write them in the live Q&A. In the meantime, I guess one question I have is whether clouds and snow or shadows affect the accuracy of that detection. Is that a problem, or how do you deal with that?
Yeah, that's definitely a big problem, actually, especially here in New Zealand when looking at satellite imagery, especially optical satellite imagery that is affected by clouds quite heavily. The usual approach is that we just mask out everything that is covered by clouds and also by cloud shadow, usually, because it's really difficult to detect objects in those regions. So we like to transition our pipeline also to a deep learning approach to detect those sort of regions. But so there are a couple of techniques that we could try out to map objects in shadow areas, for instance, or in hazy areas, which are not quite thick clouds, but so we're working on this.
Excellent. One question that came from Joseph Crossland. He's asking, did you have challenges with imbalanced data sets?
Yeah, that's a really good point. And we experimented with that a lot. So we've implemented, or Alexander Amy's, my colleague, implemented a couple of accuracy metrics and loss metrics that are considering balanced accuracy or balanced statistics rather than overall accuracy metrics. So that's definitely, I think you should watch out for during the training stage. And we usually work with quite imbalanced data sets where lots of the classes are zeros or not labeled. So that's a really important issue, or really big issue.
Excellent. One more question from Daniel Bentel. He's asking, did you have to do any special handling to use 4+ image layers? So I'm guessing you're using satellite data, and so you have different channels. You have more than 4 channels. How many channels do you have actually?
I think in the original TensorFlow functions, it only supports 4-band imagery. So we have our own custom generator classes and also augmentation routines, and they can ingest as many bands as you want, or as we want, basically. So we tried it out on 20 bands, and even more than that, I think. So it's definitely possible, but you have to either write custom classes for that, or I also saw that on GitHub there are a couple of packages that specifically cater for multi-band or hyperspectral imagery.
Excellent. Thanks again. Thanks, Jan. Thanks, Deepak, for the presentation this afternoon. And now I'd like to introduce Georgina Ray from NZRSE, who is going to close the conference. Georgina, of course, is well known by me because she's heading the CST computational science team, and she's very involved in engagement and conferences, as well as on anything that has to do with RSEs and first sort of software principles. Thank you.
Ngā mihi nui, Alex. Tēnā koutou katoa, ko Georgina Ray toko ingoa. Hi everyone, my name's George, as Alex said, and Science Engagement Manager here at NZRSE. And I guess in that role, I've had the privilege of watching this event and the Aotearoa New Zealand RSE community really go from strength to strength over the last few years. It was great yesterday to see Nuria and Manadeep's slide, which like literally showed the numbers growing over time. That was from the metrics BOF yesterday afternoon. But it's also really great to see more and more engagement, more and more conversations happening around the place. So something that we looked to achieve when we first got this conference up and running again in the when was it? About 4 years ago. I did want to reflect a little bit on timing. So the timing of this event has fallen well and fallen badly in different ways. So of course, level 4 for Auckland and level 2 for other areas around the country mean that we haven't been able to get together in person. So that's a real shame, but thank you to everyone who's managed to get this online platform working so smoothly. It's been a fabulous event from that perspective and has enabled all those conversations, I think, to happen despite that. It's also International RSE Month. I'm going to butcher this, but SeptemberSE. Yeah, so all sorts of activities happening around the world this month, and I don't know whether that was very clever planning or wonderful luck, but regardless, it means that the conversation around RSEs and careers and recognition and all those really important things is really top of mind for a lot of people at the moment. And the other call out in terms of timing is Te Wiki o Te Reo Māori, Maori Language Week. And I've found it really impressive how many people through the course of this event have, whether confident or not, had a really great crack at using Te Reo. It's a wonderful forum and stage for it, and hopefully you guys will enjoy the rest of the week testing out listening, reading, singing in Te Reo. So some reflections on the last couple of days. There's been 30 odd speakers, more than 100 attendees, I think over 70 in some sessions, and not much lower than about 45, I think, in most. So it's really been a fabulous turnout. The theme, how to create effective collaboration through implemented workflows, accessible data, and community building. I think we've ticked all those boxes. I hope we have. I've heard bits and bobs across that. I think we started off in a fabulous sort of way with that Snake Make workshop on Wednesday. So thank you to Leah Kemp, who really did the hard yards there, supported by some of the NZRSE team. In terms of conversations and topics, we've traversed all sorts of things. There's been the technical implementations that we have come to expect from this event, through to how to make it easier for researchers getting started, Māori data sovereignty. I really particularly found that talk interesting. The comparison of what's Māori data sovereignty versus Indigenous data sovereignty was something I hadn't really reflected on. So something for me to take away and think about. Career recognition, and of course the demos. Love the demos. And throughout, there's been heaps of questions, heaps of engagement and discussion, and even within the the Slack channel at NZRSE, heaps of offline discussion about what we've heard and the cool research that's going on. So really impressive there. Now we need to do some thank yous. Ngā mihi nui. The organising committee. There's been huge contributions from a bunch of people, and in no particular order. Thank you to Janet Stacey from ESR, Alexandra Pavlik from Manaki Whenua, Alexander Pletzer from NZRSE and NIWA, Manadeep Sinha from Swinburne University, Yvette Wharton from University of Auckland, Lena Neem from University of Auckland, our fabulous event organizer. And last but not least, Megan Gidry and Nuria Lohani from NZRSE as well. So huge contributions from right across that committee. And I have heard about how committed the committee members were, and it's really appreciated. So well done on a fabulous event. It's also been supported, this event, by the RSE Australia and New Zealand Steering Committee. So thank you for that. And of course, all of you. So thank you to those that took the time to pull together their presentations and share what you're doing with the community. It's what it's all about. And for all of you who have attended and asked questions and taken in all that information, that's also really important. Finally, where do we take these conversations from here? So there's a few things happening that you guys should keep in the back of your mind. I know there's a variety of working groups that have been flagged through this event, things like the machine learning ops, cross-CRI conversation. There's working groups around some of the research software, FAIR principles and citation work. There'll be others that I have already forgotten, sorry. But yeah, keep those sorts of groups in mind. There's eResearch Australasia, where many of these conversations will continue. That's next month, online. And eResearch NZ, so NZRSE's hosting that event in February next year, hopefully in Christchurch, hosted by the University of Canterbury. But if not, we'll see you online for that event as well. And your final chance to connect with all your colleagues here is at the networking event, which is running in 15 minutes. So that's the last networking event of the conference. So that's all from me. Thank you so much for attending, and thank you so much to everyone who's contributed and made the event what it has been over the last couple of days. Ka kite anō.